Hello, I'm Nicholas Petela, and I'm here to tell you guys about some of the work I've been doing with the neuropsych department with Dr. Bozer. This is Neurons, Real and Imagined. So basically, you have this device called an EEG, or an electroencephalogram. It has these electrodes at the scalp that measure postsynaptic potential of the brain. And after we get the electrical signal that's coming out from the brain, the sensors measure it, and then we can do some analysis to try and figure out where that signal came from. However, this has some problems. The electrodes are very sensitive, and so the data doesn't come out nice and pretty. Overhead lights and blinks, any sort of muscle movement in the face can influence the signal, and the equipment gets jostled occasionally. So I worked on developing the data pipeline they were using. They use eye motions to move the data from the EEG onto the computer, and prior to this, they used a bunch of manual cleaning with EEG Lab. After I came in, we started using MNE Python, which will replace EEG Lab for data management. We can also implement any sort of algorithm we can read in a paper, so we can have a more modular pipeline. And it's also free, which lets us share it with outside collaborators a lot more easily, and is just better practice. So first things first, we had to do some easy stuff with pandas, coercing the data out of the native format into something Python could handle. And we used MNE to perform a bandpass filter, and we also built out the back end of the analysis pipeline. However, we still need to remove those artifacts from the line data and the eye data. So this is independent components analysis. It's analogous to what principal components analysis is for tabular data. So basically, each one of these is a map of a certain component of the brain activity. So an expert would read this and see that ICA 0, 3, and 5 are all brain components, where ICA 9 and 12, because of their focus in the front of the face, are more likely to be muscular in origin. So we want to clean those components out and extract them and hopefully get some better data to work with. How do we do that? Well, what I did was apply ResNet34, which is a common image recognition algorithm, on those pictures I showed you a second ago to locate the different types of components, brain, eye, and line. And initially, we were getting some pretty decent results. The eye and line artifacts were being discriminated correctly. However, I discovered we had a leak in our data, and so I fixed that up. After fixing the data leak, I also decided to separate it into two separate categories, brain and other. Both of these are non-artifactual in nature, so we want to filter out eye and line data. And after performing that split and fixing the data leak, I was able to improve my accuracy significantly. However, we're not concerned whether it's eye or not. We're concerned whether it's artifact or not. So currently, we're getting about 88% accuracy, and we're erring on the side of caution, picking artifact more often than not, when it is the case. So we're actually over picking EEG, which is good because we can manually filter out those remaining components. Future directions, I hope to expand this out to also account for the temporal data. Currently, I was just using a data set that I myself had hand labeled, so I also need to get some experimental validation from neuroscience people as opposed to math people. And I also want to build this out into a full semi-supervised pipeline that will let us refine the model as new data comes in. Thank you to the Tarleton Behavioral Neuroscience and Psychophysiology Research Group for the data and helping me with this project. Thank you for the Tarleton Math Department for teaching me how to actually do data science and for running Math Day. The photo credit from earlier is Kurt Magoni, and if you have any questions, feel free to contact me via my email.